All right, thank you everyone for coming. This week we've got Dr. Ricarda Beckmann, University of Cambridge and fellow at Newnham College, giving us a talk. Her research focuses mostly on black holes, ranging from their origin to their impact on galaxy evolution. Should be a really interesting talk this week. So I hope you all enjoy. Over to you.
Thank you. So hello, everybody. I've heard I've spared you a rainy journey out across Cambridge, so it's probably a good thing. Today I want to give you a brief overview on what I mean, what it is I study, why I study it, and where some of these sort of ongoing problems in the field, I suppose, that me and many other people are currently working on. So the coevolution between supermassive black holes and galaxies. Start with the basics. What is a black hole? So the Oxford English Dictionary defines it as an object with such a strong gravitational field that its escape velocity exceeds the velocity of light. So there's a really nifty way of sort of visualizing that. And that is if you imagine you're holding a ball and you throw it up, it will go up a certain amount and come back down. If you throw it faster, it'll go higher. But there's a point where if you'd be able to throw it hard enough, the ball would be flying so fast when it leaves your hand that it will never turn around. It will escape the gravitational pull of the Earth, and this is what we call an escape velocity. And how fast this escape velocity is depends on the gravitational potential of the object that is that you're trying to escape. So here's a sort of very simple visualization of this. The idea is that the heavier the object, the more it is distorting space around it, the deeper the potential, so the faster you'd have to throw it to get out of it. So, but the escape velocity doesn't only depend on the object you're trying to escape from, it also depends how close you are to the object. So if you've already traveled a certain amount of distance away, you're less deeply in the potential, so it's easier to be escaping. So for example, if you're at the green position in this little diagram, you have the shallower gravitational potential value, you have a lower escape velocity. If you're at the red point, you're deeper in the well, so you'd need a higher escape velocity to get out. Generally, the more massive the astrophysical body that's doing the distorting, the deeper the well close to the object. Escape velocities depend on the mass. Like I said, for example, from Earth, we're looking at about 11 kilometers a second on the surface. Now, if anybody goes, why do rockets escape? Well, because they keep being powered, so that the other way to do it is to continue injecting energy as you go. But if you were going straight from the surface without any extra propellant, you'd have to go at 11 kilometers per second. The moon is smaller, so it's about 3.5 kilometers per second. Anybody remember the Rosetta mission and the unpronounceable comet? It was very small, so we're looking at more like a meter a second, so considerably smaller than something like Earth. That's about 3.5 kilometers an hour, or less than walking speed. This was actually a challenge for the mission because they were worried that if they bounced their lander too hard and it bounced back too fast, it might very easily bounce off the comet. Thankfully, that didn't quite happen. And then what is a black hole? Well, it's an object that is simply so massive that its escape velocity is higher than the speed of light. So 3 times 10 kilometers per second. So ultimately, a black hole is just an extremely heavy object that distorts space-time very far, but it gives it a few funny properties. The first one is that there's this point when the escape velocity becomes the speed of light. So if you're too close to the black hole, you're too close to, this is sort of roughly the structure of what we think of as a black hole. In the middle, we have a singularity. That's where the mass is, we think. And then around it, there is mostly empty but very distorted space. If you're too close to the singularity, the escape velocity exceeds the speed of light. But as you are going further away, like with any other object, you're getting somewhere out of the potential. So there's always a point that you reach when the escape velocity locally where you are becomes the speed of light. That is what we consider the black hole's event horizon. So if you're outside that, so in this little diagram, above the sort of pinkish line, your escape speed is lower than the speed of light, so you're no longer in the black hole. If you're inside that, you are in the black hole because you cannot physically go fast enough to ever escape, as nothing can go faster than the speed of light. Now, this is highly simplified, obviously, but it sort of covers the gist of what makes a black hole a black hole. It's for a non-spinning black hole only, so sorry, the little illustrations that I should have used. If you're too close, even light is not going fast enough, so it effectively turns about, it is trapped. If you're far enough away, light can escape. And these black holes, because they are ultimately quite simple objects, they only really have 3 properties. They have a mass, They theoretically have a charge, but we think all astrophysical black holes are uncharged, so that's not one we very often think about. And they have a spin, so the whole object can be rotating, which gives a spin axis and a spin magnitude. If the whole thing is spinning, it's a little more complicated than the simplified diagram here, because you end up with sort of different areas, depending on whether you are along the rotation axis or perpendicular. You end up with a second region called the ergosphere around the event horizon, which creates another is an area where the space-time is being dragged. Well, it's being dragged everywhere, but it's particularly being dragged in the ergosphere. So that creates another sort of funny region that around the black hole. But in principle, even a spinning black hole remains a very simple object. Oops. So a black hole is an object with such a strong gravitational field that its velocity exceeds the velocity of light. From our point of view, when we're looking at coevolution later, the important thing will be that black holes only ever get more massive. I know that's not technically true. You can have Hawking radiation, which might carry away some of the mass, but on the timescales we're looking at and for the kind of black holes we're looking at, they only ever get more massive. Once things fall in, they never come back out. Astrophysical black holes fall into three categories, categorized by their masses. We have so-called stellar mass black holes. As the name suggests, they're about the mass of a star. Then we have intermediate mass black holes. I'll get back to those later in a bit of detail. And when we think about the coevolution with galaxies, we typically think about supermassive black holes, which is the most sort of massive category. So really, we're just taking black holes. They're all structurally the same. We've just sorted them by mass. Stellar mass black holes are the kind of objects we've been seeing lately with the LIGO detector. They tend to be sort of the ones we've detected are of the masses of a few times to a little over 100 times the mass of our sun. But they certainly have a very limited mass range. We think they're probably very common. They're just very hard to detect. Like all black holes, we can only detect them when they're interacting with something. So when they're either accreting gas and growing or when they're merging. So we think there are lots of stellar mass black holes there, but most of them are probably not doing anything. So they're very hard to find. Supermassive black holes are sort of at the opposite end of the mass scale and are really quite extreme objects. A typical supermassive black hole weighs as much as an entire small galaxy. So here we've got a picture from NGC 5477. It's a dwarf galaxy. So for a galaxy, it's fairly small, but it has weighs about 1 billion solar masses, which is about the same as a supermassive black hole. That black hole takes all that mass, which can form an entire galaxy, and squashes it into the size of about the solar system. So about 10 to the 9 solar masses, I think would sit within sort of the orbit of Jupiter if you sort of scaled it down to the mass of the to the sort of if you place the black hole at the center of where the sun is, then the event horizon would be roughly out, I believe, somewhere near Jupiter. So you end up with an object that weighs the same as a galaxy, but in the volume of a single planetary system, which is why black holes are some of the most extreme objects in the universe and create some quite interesting effects that can have an impact on their host galaxy and on the universe far beyond sort of the physical volume they occupy. So what do we mean by the coevolution between black holes and galaxies? It's the phenomenon that massive black hole growth and galaxy stellar mass growth are very tightly linked, and that neither black holes, or by that I mean neither supermassive black holes nor galaxies, would look the same without the other in the universe today. So black holes technically anything can become a black hole. You just have to squash it strongly enough. But to give you an idea just how strongly you'd have to squash it, if you wanted to turn the Earth into a black hole, you'd have to take the whole planet, squash it down to about the size of a pea. And then you'd have enough mass and a small enough region to have an escape velocity that's high enough that you'd be able to escape, that you'd be turning it into a black hole. Now, obviously, the mass would be the same, but the Earth is quite extended, so you can never get close enough to the mass to have this problem. If you stood on the surface, like I said earlier, the escape velocity is more like 11 kilometers a second. There's not many sort of, places this can occur, like a planet isn't going to spontaneously collapse because its gravitational pull is being counteracted by the atomic forces between its particles. But there are some areas in the universe when we can have sufficiently strong collapse occurring to squash a lot of mass into a very small region and turn it into a black hole. One of them is massive dying stars. Another one are very pristine gas clouds in the very early universe. And there's some suggestion that overdensities in the first seconds of the universe might also have created black holes, but the jury on that one really is still very much out. So, but all these ways you make a comparatively small black hole. You might get a few tens of thousands to hundreds of thousands solar masses into a black hole in one go if you have a very extreme setup in the early universe, but that's still many orders of magnitude away from the billion or 10 billion solar mass black holes that we see today. So if you have a small black hole, how do you make a big black hole? You throw stuff into it. And you can throw all sorts of different things into it. It doesn't really matter. Once it goes in, it just makes the black hole bigger. Typical things are other black holes. We call these black hole mergers when two black holes merge. Neutron stars, but sometimes stars themselves. This is called a tidal disruption event. But typically, the way that most black holes grow over long periods of time is that they simply accrete free gas from the host galaxy around them. So galaxies consist of stars, but they also contain a lot of cosmic gas in these sort of vast clouds. That gas forms stars, but it also can fall into the black hole, and if it falls in, it adds to the mass, making the black hole bigger. The problem is that, you know, to get to the point where we need to be today, if you start with a stellar mass black hole, which are the best sort of observed black holes we have, the small ones, and think, okay, in the early universe there were stars, these stars died, they left stellar mass black holes, and you try to grow it into a supermassive black hole. Order of magnitude estimate, you'd have to take something about the weight of a sesame seed and turn it into the weight of a smart car to get the mass ratio between where we think it might have formed to where we see them today. There's some ideas you could make more massive black holes, but even then you need to grow them by at least a factor of 10 to the 5, 10 to the 6, or add 5 or 6 zeros to the end to get to where we need to be today. So it's quite an extreme process. It goes on across the history of the universe, and one of the questions we've been trying to understand for a long time is how black holes even manage to grow so massive. That's something I will mention later again. So where does that leave us with coevolution? Black holes, like we said, have to grow a lot, and while they do it in galaxies. So black holes live in galaxies. This is a picture from a computer simulation of a galaxy, and galaxies are full of gas, which is what's shown here. The gas sort of is clumpy. It forms these denser clouds. This is the cartoon image. That's not actually what it looks like, but so you get dense clouds of cosmic gas forming galaxies. These clouds are also where the galaxy forms stars. So for star formation, you need very dense gas. So it tends to be these clouds. But some of these clouds also fall into the black hole. This is how the black hole grows more massive. You could imagine how sort of, the amount of gas in the galaxy and, controls both star formation and the growth of the black hole in this context. But actually, there's a much more direct and tight link between galaxies and black holes. And it's something to do with how an extreme an object a black hole is. Because as some of this energy falls, some of this gas falls into the black hole, because it's such an extreme potential, it doesn't fall directly in. Some of it will circle the black hole in so-called accretion disks. And in the process of trying to fall into the black hole, a lot of energy gets released. So effectively, the black hole converts a certain amount of the mass that falls into energy, which is then re-ejected into the galaxy. So it can be in the form of photons, it can be in the form of hot winds, it can be in the form of jets, but either way, a lot of energy is being released by black holes. So ironically, black holes, despite being called black, are some of the brightest objects in the universe when they're active, because a lot of mass is being transferred this way, which means a lot of energy is being released potentially. This energy goes back into the host galaxy, it interacts with the gas, and in particular interacts with the cold, dense clouds that both feed the black hole and that cause the star formation. So it tends to either evaporate them, it tends to eject them, but if you have a lot of this energy injection, these cold clouds in galaxies tend to disappear. Star formation turns off, there's no more fuel to do it with, all the gas is too hot and to diffuse to form stars, and also the accretion onto the black hole tends to turn off because it's fed by the same cold clouds. As a result, the energy injection from the black hole turns off because it's directly linked to its growth rate, and over time the cycle can start again. So not only are star formation and black hole growth drawing from the same sort of supply, but the black hole actually regulates the availability of that supply in the galaxy through this energy reinjection. So the feedback from the black holes controls both the stellar mass growth and the black hole growth in the galaxy through this sort of cyclic setup. Now, how do we know all this? Well, one of the big problems is that in astrophysics, it being observational science, we are a little short on experiments. So it's not, we typically cannot experiment. We typically cannot even see objects evolving. Galaxies, for example, evolve in such long periods of time. If you looked at them today and you looked at them even at the end of a human lifespan, they would look effectively the same. So the best thing we have to understand how all these kind of processes play together, what impact they have, is to use computer simulations. And this is also where my work comes in. I do large-scale, what are called cosmological simulations, as well as some smaller scale stuff to try to understand how black holes and galaxies co-evolve. The details of that link, the impact on the galaxy, the impact on the black hole, and all the important components of it. So we use computer simulations as experiments. I'm going to show you a video of the kind of simulations I work with in a minute. But before I do that, I want to quickly show what you're going to be seeing. So this is a still from the movie I'm going to show you in a minute. What we see here is it's a very large scale view. Every one of these little dots is a small galaxy, effectively. So what we're looking at here is the cosmic web, large scales. It's the gas density in the universe. You can see the overdensities forming where the cosmic web is, and these sort of knots where the galaxies are. And what we have here, so in blue, we have the density. Light blue is dense, dark blue is diffuse. And then we're also showing the temperature, because this is going to be important in a minute, where you see these hot bubbles around the galaxies. And that's where black holes and also stars are injecting energy in the kind of method I showed you in a minute. And you can see how this energy is going to sort of propagate outwards from the galaxies as the simulation goes on. So this is a way where we've taken the sort of what we think we understand about the black hole physics, how it converts mass to energy, and put in a simulation, and now we're going to evolve it forward to see what happens to the galaxies. So if I set that running, which I hopefully will do. Yes, there we go. You can see that, from this is from sort of the very early universe, you can see the densities building up as everything collapses and continues to evolve. Cosmic web is evolving. You can see these galaxies forming here, all these bright knots, and you can see a lot of energy being injected from the centers of the galaxy. Some of that stays in the galaxy, some of it is being injected to much larger scales, but it's creating these sort of hot gas structures in and around, in particular in this galaxy for this particular example. So this is, as I said, low redshift, so roughly how the universe would be today. And this is just one example galaxy that we've modeled using what's called this cosmological simulation. Cosmological simulation means it's got all the context of the cosmic web, all the other galaxies, the evolution across cosmic history. And the powerful thing about these cosmological simulations is that we end up with not just one galaxy, like I showed you here. This was sort of a zoomed in view so you can see what's going on. But actually, there's a really big box with lots of galaxies, all connected, all in their right place. So what we can do is we can extract effectively a sample of galaxies from this, which have been modeled using everything we put into the simulations. And we can not only do it today, we can look at the evolution of the same object across cosmic history, which is something we could not do with observations. With observations, we can look back in time. You've maybe heard about some of the JWST results, which is currently sending us images of galaxies from the very early universe. But the problem is we can never, there's a lot of guesswork involved in trying to figure out what the things we see at the time turn into today, because there's lots of types of galaxies at the time, lots of times today. And we can never see the same object changing, which is very useful if you're trying to understand if something evolves. Whereas with the simulation, you can. For example, here we've got a little sort of set of images extracted from the simulation I just showed you. And each column is just a different point in time, but it's the same galaxy over time. You can see here it says log m, so that's the log of the mass of the galaxy. You can see it gets more massive over time. So we go from early universe to more today. You can see it becomes more settled. It's very sort of fuzzy, whereas here it has much more of a spiral structure. This is in the gas, and the same is obvious in the star. So it goes from this sort of clumpy, blobby galaxy in the early universe to something much more settled today. This is just the same thing, but looking at it edge-on rather than face-on. That's the other advantage of a simulation. You can look at it from any angle you like, as opposed to in an observation where you get what you get, and sometimes you really wish you could turn the galaxy around. So we get a lot of information from this on the galaxies, both in terms of a time evolution and in terms of the properties we can look at. So over here, for example, we've simulated the gas mass, the stellar mass, the gas temperatures, how fast it's rotating, how old the stars are, all these sorts of things, which you can just pull straight from the simulation and then study to try to understand how we think all these different components that drive galaxy evolution play together. So this is a sort of a little aside, I suppose, on the scientific method. So what have we learned from looking at these kinds of simulations, from looking just at the universe straight up, and how we think coevolution, this link between massive black holes and galaxies, shapes the universe? So the first view is something from observations, and probably one of the key things that set people down on this path of trying to understand whether there really is a link or what the link is between black holes and galaxies. This particular plot is from McConnell 2013. There are earlier versions. And what we have here, this is an observation. So people have gone out and looked at real black holes and real galaxies rather than relying on the simulations. And they've simply plotted for each supermassive black hole that they've found in the local universe on each galaxy. They've plotted the mass of the black hole on the y-axis versus what's called the velocity dispersion of the host galaxy on the x-axis. So this is a measure that measures, it's not quite the mass of the galaxy, the stellar mass of the galaxy, but it's a measure that sort of goes in a similar direction. More massive black holes are here, more massive galaxies are over here, lower mass galaxies will be over here. And again, low mass black holes are here, high mass black holes are here, and you can see there's a very tight link between them. So low mass galaxies host low mass black holes. So far maybe so obvious, but it's just the fact that they're actually so tightly correlated. If it was much less of a tight link between them two evolving, you'd expect much more scatter in this plot than we are in fact seeing here. So that was one of the first sort of key evidences from observations that made people think, I wonder how the two are linked and whether they are in fact co-evolving, or whether this is, what drives this very tight correlation that we see in the universe today. And then they turned to simulations to try to understand this. This is a plot from one of my papers from 2017, where what people then did is they modeled the kind of cosmological simulations I just showed you, but the early ones didn't include this energy injection from the AGN. It had black holes in it, but the black holes weren't injecting energy. So they weren't converting mass to energy, because people had seen some of that in the universe, but they didn't think it was necessarily important. Then it became clear that this might be very important, because what happened is when people looked at, so they ran these big cosmological simulations, they extracted all the properties of all the galaxies they had in there, and then they compared it to the real universe. This is typically what we do to try to understand whether we've put everything relevant in the simulation, and to see whether, which is then a sign that we've possibly, hopefully understood something about the process. So when people did this to start with, what ended up happening is that they vastly overshot. So what we got on this plot is here we've got this is like a sort of histogram of the galaxies in the universe. So we've got the galaxy stellar mass on the x-axis, and on the y-axis is effectively a number count. So this counts, how many 10 to the 10 solar mass galaxies there are in the universe. And this blue thing is the observation. This is what the real universe looks like. And early simulations had a problem in that they vastly overshot, especially at the massive end. So if you ran your simulation, you found in your simulation block galaxies, you found too many massive galaxies. That was the first problem. And the second problem is that some of them were more massive than any real galaxies we've ever seen. So clearly the galaxies in the simulation were growing too fast or too much in comparison to what happens in the real universe. And it was only when people added in this energy injection from black holes, which is a second simulation with a different model now including this energy injection, that the number counts of galaxies in the simulation box started to look significantly more like what we see in the actual universe. So you can see it's now, it's not perfect, especially down here, but the error bars are also pretty big and the observations cut off. But we are starting to sort of hone in on galaxies that look much more like what we see in the real universe. So what this tells us is that this energy injection is one of the key processes that drives the evolution of particularly massive galaxies, and it slows down their evolution. So it turns off star formation, regulates the star formation in massive galaxies. So the reason they look the way they do today is because their supermassive black holes have, dampened their growth over long periods of time. The other thing that people found using these simulations is that if you don't have this energy injection from the supermassive black holes, your galaxies don't look right. So this is from a slightly older paper from Dubois 2016, where again, there are two sets of simulations, one with the energy injection, one without. And they basically looked at, and they modeled the same sort of volume of the universe, if you will, so that you could take your two simulations and basically say, okay, this is the same galaxy in the two simulations, one's with the feedback and one's without the feedback. And this is exactly what they did here. They found the same galaxy at the same sort of location in the cosmic web. So that tells you it's come from the same initial overdensity, and you would expect it to, evolve roughly the same under the same physics. And then on the left, we got what the stellar distribution looks like. So this is sort of like for example, if you observed it with Hubble, roughly, this is what you would be seeing. On the right, you have it without active black hole, so without the black hole feedback, and on the left, you have it with the active black hole feedback. And what they found is that basically without active black holes, virtually every massive galaxy was a blue spiral. Now, in the real universe, we see some massive blue spirals, but we also see an awful lot of massive elliptical red and dead ellipticals. And it was only when you added these active black holes into your simulation and included that as part of your model that the simulation started producing massive red ellipticals. So it's not only the feedback injected from these black holes not only produced, changed the total mass of the galaxy, it also changed the structure. Blue galaxies tend to have a lot of younger stars, so that's a sign that they kept forming stars in these sort of disk-like structures. Whereas with the black holes, a lot of that late star formation in particular was prevented, and the galaxies looked more like these sort of round, spheroidal-shaped red galaxies, which means they were dominated by older stars. So the shape of them changed, the stellar populations changed, and with the black holes in the simulation, you started seeing much more realistic samples in comparison to what we see in the real universe. So again, that tells us that this energy injection from the black holes is a really key component that shapes how galaxies look today. So that was sort of a crash course on probably the three sort of major results that have come out of this. But obviously, this is a big field. It's basically tied into galaxy evolution. There are lots of different types of galaxies. People try to understand and continue to try to understand all sorts of parts of this process, because while we have a really firm understanding that it's really important, I think we've nailed down a lot of the sort of really key components of it. The whole process is quite complex. It's different in each galaxies. There are various different assumptions you have to make in your models, and we're still very much trying to understand the details. We're trying to understand how you model a black hole is important. I'm going to go through a few of the sort of open questions, I suppose, where there's a lot of ongoing research, but I want to make it very clear that this is a really big field. There are lots of people who are working on this in some form or another, and I can only give you effectively a fairly brief overview onto some of the questions. I've chosen to pick a few questions that I'm working on in some capacity, because part of the brief I was told it was to present you some of my research. So, this is all I want to say is this is by no means exhaustive. So one of the key questions that people are asking themselves at the moment is, where are the intermediate mass black holes? Earlier I said there's three categories. We have some observations for the stellar mass ones. We've got observations for the supermassive black ones. But there is, or has long been, a bit of a gap in between. So again, this is the plot I showed you earlier, just a slightly more modern version from a review by Jenny Green in 2020. We got the massive black holes here, 10 to the 10, that's the really massive end. And you can see that the observations that we have, which are these sort of circles and squares that we got here, sort of tail off, probably around 10 to the 5, 10 to the 6 solar masses. If you remember the stellar mass black holes, they would be down here. They would be maximum 100, maybe a little more. So they would be all the way off the bottom end of this plot. And there's this sort of glaring hole in it. This is what we would call the intermediate mass black holes, but despite a lot of efforts, it's only very recently that we're starting to get a few observations of black holes in this mass range. For a long time, it wasn't clear whether this exists at all. You could imagine a universe where it isn't, where black holes have either started growing very efficiently early on, so all the black holes that grew are supermassive today, or they haven't grown, in which case they're still stellar mass, so you end up with a gap in the middle. Or, probably more realistically, you would expect there to be some sort of continuum from the lowest masses to the highest masses, and then the question is, where are they, and why can we not find them? In recent years, people have started finding them. We don't have as many as we do for the supermassive black holes. They're a lot more challenging to find. Their galaxies are smaller, they're much dimmer, they have a much smaller sort of what we call sphere of influence. So one way to detect a supermassive black hole is to look at the stars that are close to the black hole. But that sort of volume that we would consider close is a lot smaller for a smaller black hole, so it's much harder to do with a telescope. So there are good reasons why we might not have found them, even if they exist, but we are now slowly starting to find them, possibly. But the question of how many there even are is still very much open. That's one thing that I tried tackling with simulations reasonably recently. I should have had a quotation here. This is from last year, this paper. Oh yeah, no, it is there, Beckmann 2023. where I used a simulation that particularly looked at low mass galaxies. So we can target our simulations slightly differently. If you want a lot of massive galaxies, you're probably going to end up with a very big box. But the problem is big boxes are expensive. So what you typically do as trade-off is you increase your resolution. It's a bit like a photograph. Our simulations are effectively 3D pixelated in some way. And if you want to make the whole thing bigger, and you only got a certain amount of storage space, you're going to have to trade it off by making the pixels bigger. The alternative is what we did here is we focused on a smaller volume of the universe, but we added much higher resolution, which means we could look at smaller galaxies. Because if you turn down the resolution, what happens is that your low mass galaxies disappear from your sample because they're just completely unresolved, or at least completely unreliable. Whereas here we targeted the lower mass galaxies because we think, there's this link between galaxy mass and black hole mass. So if you're looking for low mass black holes, we need to look at low mass galaxies. And what we found is that in our simulation, in fact, plenty of low mass galaxies do in fact have a central black hole. So what I've done here is I've gone and looked at all the galaxies in the simulation, and I've counted what fraction in each mass bin contains a black hole in the center. So this doesn't say anything about the mass of the black hole. The ones in the more massive galaxies are also more massive, but it's just a sort of a number count. What you see is that for the massive galaxies in this sort of gray shaded region, they virtually all contain a central black hole. So the fraction that black, has one is roughly 1. If you go to the lowest mass galaxies we had in our sample, it goes down to about 50%. So about every second galaxy will in fact contain a central black hole. But that's still actually quite a lot. And especially in this intermediate range, you would expect the majority of galaxies to contain a central black hole. So what this tells us is that there should be a lot of intermediate mass black holes out there, because actually the lower mass galaxies are much more common than the massive galaxies. So, if you account for how common the galaxies are, you'd expect a lot of intermediate mass black holes. The problem is that they're very hard to be seen. So one of the things we did is we looked at our simulations, and like I said, we modeled the energy injection. If the energy injection determines effectively how bright the black hole is, so how easy it is can be seen through a telescope. So we looked at, how bright the black hole is. In this case, we used X-rays, so we sort of modeled how many X-rays we think the black hole is emitting, and we modeled how many X-rays we think the galaxy is emitting. So the first problem we have, and we discovered with these low mass black holes, is that typically the galaxy is brighter than the black hole. So this dashed line here is where they'd have the same brightness. So these two dots, the black hole and the galaxy, are about the same brightness. The problem is anything below here, the galaxy outshines the black hole. So then you're trying to, see a candle in front of a very bright light bulb or something, which is extremely difficult to do. These crosses here look promising, but unfortunately, they're all the massive galaxies. So if you're looking at the low mass galaxies, which are the dots, you can see the vast majority are down here. And in fact, there's only very few examples that are actually, where the black hole is brighter than the galaxy. And they typically have comparatively low luminosity. So the higher you are on this y-axis here, generally the easier it is, the brighter is the object overall. But because these objects are lower mass, they're also generally dimmer. So they're dim, and only a few of them are even brighter than their galaxy. So they're hard to see in the first place, and then they're even harder to differentiate from their host galaxy, which is why it's so difficult to see them observationally and why we're having such trouble trying to find them. But the conclusion from this is that the fact that we can't see them doesn't mean they're not there. They're just very, this confirms a theory people had for a long time that they're very hard to observe. Another puzzle to do with supermassive black holes is to do with the very first supermassive black holes. So black holes, today, when we look around ourselves, we see them across a range of masses, 10 to the 6 or 10 to the 10. And you could sort of conceive of saying, okay, if you go back in time, you'd expect the most massive ones to be less massive, so maybe it goes down to 10 to 9, 10 to 8, 10 to 7 if you go back in time. And that's true to some extent, but actually what people found is that the problem we're having currently with our black hole growth model is that you can go pretty far back in time and you have some very massive black holes. So what we have here is a plot that sort of effectively shows like an evolution history of, it shows us looking back in time at different times and just looking at the masses of the black holes at the time. Today is here, all the way on the left. That blue arrow there is the Milky Way, which is, this Sagittarius A star. It's our closest supermassive black hole. It's pretty puny. You can see it's fairly low in this plot. M87 has a really massive one. It's also very nearby, so it's up here. Then, as you go back in time, you will notice that there's massive black holes, so up to 10 to the 10 solar masses, all the way to the very, very early universe. So at this point here, the early universe was only about 1 billion years old, and the most massive black holes at the time, they're almost as massive as the ones today. Now, before somebody asks me why do they seem to get more massive as we go back in time, that's an observational bias. As they go, as we look further back in time, we're effectively looking further away. So the object that we're trying to see needs to be brighter for us to be able to see it in the first place. Something we can see very nearby, if you remove it very far, would be too dim for us to see. So we're looking back, we can only see the most extreme and the brightest objects at the time. So essentially, we expect there are a lot of black holes down here, which we just aren't able to see. So it's not like black holes get more massive back in time. On average, that's not true. But what is true is that looking back in time, we can find some very, very massive black holes. And they must have got there. So these objects here, the universe was only 1 billion years old. They must have grown in that 1 billion years to the best we're observing them at. And that is a puzzle, because even if we're being generous, we expect black holes, if we extend this sort of axis down, to start somewhere down here. And they've had very little time to actually grow up there, which challenges our understanding of how black holes grow, because we think we know how this works, but there are some limiting factors: availability of mass, the amount of energy being converted, slowing down the actual growth into the black hole. And so a lot of people are still trying to understand how on earth these very first massive black holes have grown so massive. And in fact, this plot is slightly out of date now, because the James Webb Space Telescope keeps finding more and more massive black holes in the early universe. So actually the problem is getting just worse and worse as far as I'm concerned. And people have tried all sorts of different things, and they've started looking particularly in detail of how the black holes grow. So there's various different ways you can model this. This is a work by a close colleague of mine, Alessandro Lupi, and he was trying to understand how some of these very early black holes grew so massive. So he was trying to use the simulation as an experiment in a way. So all these sort of dots and crosses and gray and colorful markers are all observations. So this is what we're trying to reproduce with the simulations. And then what we got here, we got his 2 simulations, one in blue and one in orange. And he looked in detail at the particular type of black hole growth called super-Eddington growth, which is where black holes are potentially growing extremely efficiently. So we thought, okay, that's great. If they can grow very efficiently, they should be able to grow very fast. If we start at 10 to the 5, very early on, they might be able to grow sort of diagonally where we see them. But as you can see, what the simulation actually tells us, that they're completely flat for ages. So they actually don't grow. And it's only when their host galaxy becomes very massive, so 10 to the 10 solar masses, that they suddenly start growing very effectively and end up roughly where the observations are. That's fine if you're trying to produce these points down here, but leaves you with a puzzle, because it's like, why didn't it grow up here, right? Why didn't it grow into this region here? So actually what this tells us is that this particular mode of accretion feedback might be play an important factor in modeling the black holes down here, but it's clearly not the solution to those up here. So the puzzle remains. We still don't know how to get the ones up there. But people are working on this, like you say, it's from this year, so this is very much ongoing work, trying to understand how particularly these very early, very massive black holes came about. And this sort of when I was talking about different types of accretion and feedback, kind of already hints at the other big sort of area of ongoing research, which is the model I showed you earlier for the coevolution was highly simplified. Black holes are simple, but they're not quite that simple. They do more than was suggested there. And one of the things we're still trying to understand is how all the different aspects of black hole physics play into this coevolution. So black holes do a lot of things. They form in the first place. Various different ideas how that might happen. They can move. So black holes are typically found in the center of galaxies, but they're not actually have to be there. They can totally wander around in the galaxy, and they also frequently do. And where exactly they are makes a difference to how much gas they can accrete, where the energy is being injected, how it shapes the host galaxy. Like I said, they spin. And that is important because how fast they spin has an impact on how efficiently they convert accreted mass to energy. So, how much energy the galaxy is being subjected to for a given sort of gas inflow rate onto the black hole. They accrete gas from their local environment. That's got a lot to do with what they can find locally and the properties or the conditions in the host galaxy. They convert some of that to jets and winds, like I said earlier, and they can merge with other black holes. So that's another way they can get massive more quickly, is if they encounter another black hole and merge, you get a more massive black hole out of it. Now, the simple model I showed you earlier mostly considers points 4 and 5, but current ongoing research is trying to incorporate all the components of what makes a black hole and what they do in galaxies to understand how all of that plays together. to produce the kind, the wide range of galaxies we see today. Again, this is a piece of ongoing work, this time from one of my papers in prep, where I look particularly at black hole spin. So black hole spin is interesting because it's a vector, so it has a direction and it has a magnitude. And one of the things we think is how fast the black hole is spinning. So the magnitude of the spin has an important impact on this conversion efficiency from accretion to energy. So one of the things I did with my simulations is I modeled not just how the mass growth of the black hole, but also the spin evolution. And here I've got a little sample. I've got 1, 2, 3, 4, 5 different black holes across cosmic time, and this is the magnitude of the spin. 1 is maximally spinning, so there's a maximum amount they can spin, and 0 is non-spinning. You can see we started all of them non-spinning. That was just a parameter choice. We could have started them wherever we thought was important, but it turns out it actually doesn't matter at all because they all very quickly spin up. And then over time, their spin changes. And what we see here is that for massive black holes today, so, us today is on the right-hand side of this plot, some of them are very highly spinning. Some of them are more sort of intermediate spinning, but we don't really see any low spinning ones at all. So all the massive black holes, what the simulation tells us, are likely to be at least intermediately spinning or highly spinning. And this has an important consequences for this conversion efficiency. So if people don't model spin, they typically have to assume something. They say, and a classic value that's used is that about 10% of the accreted mass is converted to energy. So that's this sort of black line here. But we actually looked at the distribution of spins for all the black holes we had in that simulation. So not just the 5 I showed you, all the ones we had. And we looked at, we distributed them by mass to see, if there's some sort of signal, whether the more massive ones behave differently than the low mass ones. And we looked at the value of this actual, what's called the radiative efficiency. So there's this conversion factor from accreted mass to feedback energy. And you can see that actually this guess of 10% is not particularly good for most black holes. So if you look at the distribution of the dots, most, especially the massive ones, tend to have higher feedback efficiency. Some of them are close, but many of them are actually much higher, up to twice as high. If you look at the low mass ones, you get a very wide distribution because they can be anything from non-spinning to maximally spinning to maximally counter-spinning, which produces this sort of weird bimodal distribution here. But basically for these also, just assuming a flat 10% and does not at all represent the population very well. So what we've learned from this, that I think going forward now that we know how to model a spin a bit better, and we're actually starting to have at least a few observations of black hole spin, which is one of the reasons we haven't done this so much before, we actually really need to start thinking about the spin, and maybe this changes it. So maybe, if in low mass galaxies, it can be a wide range. Some galaxies will get a lot of feedback energy early on. Other galaxies will have black holes that sit more down here that get very little feedback energy early on. Maybe that contributes something to the dichotomy of galaxies we see today. And then as they get more massive, generally they also get more efficient in converting mass to energy, which is interesting because they tend to grow very slowly at this point. But if they can convert more of that growth into energy, actually, the massive galaxies might experience more energy from black holes than we've maybe assumed so far. So now we need to sort of take this insight and sort of think forward and start, looking at this maybe from the galaxy point of view or for a different sample of black holes, because we only have a few massive black holes here, but lots of low mass ones. So again, only a first sort of glimpse, but maybe a kind of a direction into ongoing research that's happening at the moment. That was a bit of a crash course, coevolution and black holes across cosmic time. I think we have a little bit of time left, so I'm happy to try to answer any questions or try to elaborate more on any part you're particularly interested in. Thank you.
Thank you very much, Ricarda. That was really interesting. We've got plenty of time for questions, and we also have a virtual round of applause. I'll send a little clap emoji. So can you see the questions that are popping up, or do you want me to read them out?
I've seen one of them, yes. Could new physics in black holes lead to them losing mass? Yes, but also probably not. So yes, like I said, in principle, black holes can lose mass. through, the current sort of known phenomenon would be Hawking radiation. But it's a very slow process, much slower than the mass growth of the black holes we see. So for a supermassive black hole, the actual mass loss rate via Hawking radiation is negligibly small, far smaller than any growth we see. So they will always grow faster than we think they would be evaporating. So it's one of the reasons why we don't tend to model Hawking radiation, because it's not going to make a difference to our results. You can analytically work out roughly how much mass you'd be losing. So I think from that point of view, unlikely. There is obviously the problem that to some extent we don't really understand black holes. So what I've given you is essentially a phenomenological description of what a black hole is and why it works the way it does. But we do run into the problem that we have the singularity at the center. We don't understand we don't understand what that is. GR tells us it's a singularity, but also you sort of run into the problem that you're starting to deal with very large masses, which is described by GR, and very small scales, which is described by quantum. And we don't have a theory that covers both. People are still working on that. It's possible that when somebody finally comes up with some sort of grand unified theory, that it will tell us something fundamentally about black holes that might make them lose mass. I'd be surprised, but I wouldn't bet any money on ruling it out, if that makes sense. That being said, we do see very massive black holes in the universe, so they must at least many of them must predominantly grow rather than shrink. Otherwise, there would never be 10 billion solar masses today. The dark matter and intermediate mass black holes. So the reason I haven't mentioned dark matter much is because what I'm looking at predominantly are black holes in galaxies. So if you're looking at coevolution, the centers of galaxies, people sometimes ask me, do they grow via dark matter? The answer is in principle, yes, but, well, at least we think so. I mean, considering we haven't found any dark matter, but there isn't any reason that if you think dark matter is what we think it is, there isn't any reason that it shouldn't contribute to black holes. That being said, black holes live in galaxies, and the centers of these galaxies are very much dominated by baryonic matter rather than dark matter. So, the local densities, and especially when you think of the fact that they predominantly actually accrete gas, clumpy gas, very dense clumpy gas, because the denser the material they're accreting from, the faster they can grow, and they need to grow very fast. So the density of the gas that the black hole is accreting from is many, many orders of magnitude higher than the local dark matter density. So the contribution from dark matter would be very small. There is again and again this idea that a lot of intermediate mass black holes might in fact be dark matter. People keep going around on circles on this. On the one hand, it's very appealing. I mean, the idea, we understand black holes. There could be a lot of them out there. The problem is, though, it introduces two things that we should be able to look for, and people have sort of tried and failed. The first one is, if dark matter is that massive, you'll get a certain amount of granularity in it, right? Like if each individual dark matter object is 10 to the 5 solar masses, then it's not going to be smooth. You're going to have, at some point there's the black hole and then there isn't, and there is. So you'd expect some sort of granularity signature, which should express itself in other things as well, because dark matter doesn't interact much, but it does interact gravitationally, right? So if things basically should clump near where the dark matter is and clump less where there isn't any. On the other hand, if it's, say, a small particle and it's very smooth, then you wouldn't expect this clumping effect. So people have started looking for that. Not a lot of success with that. The other thing is that if dark matter is predominantly intermediate mass black holes, you'd expect not all of it, but some of it would be in galaxies, right? Like there is dark matter in the center of galaxies. It doesn't dominate, but it should be there, which means that most galaxies should contain a lot of intermediate mass black holes, especially towards the center. And you'd expect at least some of these to be active, because they would be interacting with whatever else is in the galaxy. Like you wouldn't be able to see them if they're far away, because there's not enough gas for them to grow. There's not enough for them, and probably also not a high chance for them to merge. But in galaxies, we'd expect them to grow, at least some of them. So we would be expecting to see active intermediate mass black holes a lot more than we are. People have used this to try to lay constraints on it. We do see some, but they look more like the central black holes of low mass galaxies rather than sort of, dark matter in more massive galaxies, for example. But then again, there might be the sort of brightness, problem that I talked about earlier. So But I think people have started using, or people have used this to put at least limits on which fraction of the dark matter could be intermediate mass black holes. It's very hard to rule out completely, but I think the current consensus is that it can't be all of it, because galaxies would look differently.
So, okay, looks like there aren't any more questions. Thank you all for coming. We'll be back in chemistry next week. Oh, hold on. There is another question. I'll read this one out. Could unexplained early universe supermassive black holes be black holes that began to form in time before the inflation period?
Yes, so this goes back to what we would call primordial black holes, which are ones that formed extremely early on. So yes, in principle, there are a few limits on why we think that might not be the only thing that happened. So the first issue, and this is something people are already just starting to think about, is if you, like I said, black holes and galaxies sort of control each other's growth in a sense. Now, if you imagine you end up in a situation where you have a 10 to the 10 solar mass black hole or 10 to the 9 solar mass black hole already in place before there are any stars or before there's any sort of galaxy, it's very hard to imagine how the galaxy would form around it. Because every time you have some cold gas, this extremely massive black hole would get turned on and inject vast amounts of energy and immediately turn off any sort of star formation. So really what we've learned from the simulations is that if it's quite a closely coupled process. It works well if they're sort of in relation, like on the plot I showed you. But if something, if something has a really overmassive black hole, it tends to very quickly turn off any star formation, any evolution in the host galaxy. So what you'd end up with in that scenario is a lot of naked supermassive black holes rather than what we see, which is massive black holes in active galaxies. Right, or in galaxies that have stars and are actively growing. So I think that would be one sort of issue with this. So I think the other thing sort of goes back to this kind of question about, could dark matter be black holes of various masses? If this happens, we'd end up with a lot of black holes that maybe weren't in galaxies, because the kind of theories that looked at this, there's a certain density for them to be forming. It's to do with the structure of the power spectrum early in the universe. You need certain overdensities to form certain black hole masses and such. It'd be very hard to imagine a scenario where this is an efficient process and you only get the really supermassive ones and you don't get a whole spectrum. So we'd be expecting a lot of black holes across the mass range. Again, we don't really see that. And we also don't see, we see the supermassive black holes in the centers of galaxies, but we don't see, I think there's no evidence for lots and lots of them everywhere, if that makes sense. So again, that sort of puts constraints on how they can form, and then you kind of have to come up with a scenario where certain amount of supermassive black holes that form in the early universe, galaxies form around most of them, and they happen to exactly match the distribution we see from the cosmic web structure and such. So it's possible, but it brings its own problems. It's not straightforward to say, well, the galaxies are, the black holes are just in place already and everything else forms around it, because the black holes then change how everything else evolves.
So are there any more questions from the audience? I'll give it a minute or two. Okay, it looks like that's all the questions for today. Once again, thank you all for coming, and thank you, Ricarda, for that really interesting talk. I hope you all enjoyed. We'll see you all next week in chemistry.
You're welcome. Have a good evening, everybody.
You too. Thank you very much.